we're going to talk about bulb brightness more and go over this problem. Like for the configuration seen at the right, list the order of the brightnesses of the bulbs from brightest to dimmest when like bulb A is removed from the socket or when bulb E is removed from the socket. And we're going to go through all of these. I would recommend watching my video on, what was it called? I think it's like bulb brightness intro. I don't know why I said bulb brightness intro. It'll cover the basics, and if you understand the basics, this whole thing kind of gets easier, or you can make more sense out of it. So, just as kind of a refresher, power, right, or the brightness of the bulb is connected to its power, right? How quickly it can change the what do you call it? The what's the word? Why am I blanking? Electric potential energy into light energy is determined by the power, the rate at which it does work. So power is going to equal I times V. V is equal to I times R, so it's really I times R. That's how you get P is equal to I squared times R. So each of these light bulbs have the same resistance, and that's kind of nice. You're just kind of figuring out, hey, what's going to have the most current then? Whatever gets the most current, right, is going to have the most power. So let's say when bulb A is removed from the socket. When a bulb is removed from the socket, that really means that current doesn't flow through it doesn't flow through the light bulb. There's going to be no current, essentially. I'll explain it like this. If you have current come through the positive terminal, and let's say bulb A is removed, now it doesn't know where to go. It's like, oh, there's no more light bulb to go through. No more charge is going to go through it, essentially. So when a bulb is removed, and I'll draw back that bulb, that essentially means that no more current is going to go through that bulb. You can essentially, it's almost like cutting out the wire, right? All the current's going to go through C, none of it's going to go to A if the bulb is removed. So, I don't know why I sound out of breath. Let's just draw like a schematics, like diagram of what's going on. And so we have a battery, and then bulb A is removed. So we have the C resistor, we have the E resistor, we have the B resistor, and we have the D resistor. So, these all correlate to here. And yeah, bulb A is removed, no more current's going to go through that path. You can essentially cut it out and kind of ignore it. So, now let's take a look as to what's what's going to be the brightest. So, we know kind of all the initial current. We'll say I initial is going to go through C. That's where all of the initial current is going to go through. And then right here we have a junction, right? So here the current's going to split up. So after going through C, the current is going to split up. So what I already know is that, hey, C is going to have the most. It's getting the most current here. It's getting all of the initial current, and that initial current is going to split up. So no matter what, because of the conservation of charge, we know that this current, the current going through here is going to be smaller, and the current going through here is going to be smaller. C has to be the most. So I know that, yeah, C is going to be the most. And then from here, really we have like a parallel situation going on, right? I know it doesn't look like parallel, but they're in parallel because they're both connected to this. Okay, so I should reiterate. These two, so it's B and E, are in series in this case, right? Because they're one after the other. And whatever the current this guy gets, it's going to get this, B is also going to get the same current. B and E are going to have the same current, so I know these are going to be equal. And if you think about the equivalent resistor, let's say they both have a resistance R. I don't know. The equivalent resistor in series is going to be 2R. You're adding up the resistances of B and E. So you're going to get 2R here as an equivalent resistor. And that equivalent resistor, if I were to just pretend, right, that I made this an equivalent resistor of 2R. So 2R, and then we have R. Well, they're in parallel now because they're both connected, like here, and then they end up connecting back here, right? They're essentially in parallel. So excuse me, I don't know know why I'm coughing. If I know they're in parallel, they're going to have the same potential difference going through them. V is going to equal IR. So V is going to equal I1 times R, and then this is also going to equal V, which is going to equal I2 times 2R. And this comes from Ohm's law. Oh, great. You can take a look. If these voltages are the same, then I know that I1, the current going through D, is going to equal 2, I wrote 2 times I2. In other words, D is going to have more current than B and E. So C is greater than D, which are going to be greater than B and E. They're equal. And then obviously A is going to have no brightness. It's going to be the lowest, right? There's no bulb there. All right, cool. So hopefully that kind of made sense. And we can kind of go through these next ones with the same sort of thinking. So let's draw a diagram where the E is removed from the socket. So if I were to think about that, we would have C, D, and then we would have A, B. Okay, so A and B are in series, and C and D are in series. So whatever current C gets, D also gets. Whatever current A gets, B also gets. I just draw my marker. So I know A and B are going to be equal, and I know C and D are going to be equal. So then it's just a matter of, well, there's an initial current here, right? So you know, which one's going to have more, which path will get more current, right? Well, they're going to be the same, right? Because if we think about the equivalent resistors, this is going to be equivalent resistor of 2R, this is going to be equivalent resistor of 2R. So if we think about that V equals IR, both have the same potential difference because they're connected, you know, to the same, you know, battery. They're in parallel. That's what I was trying to say. So if they have the same voltage, same equivalent resistor, each path is going to get the same current. They're all going to be equal in this case. So I know C is going to equal, I don't know why I'm doing that. C equals going to D, which is going to equal A, which is going to equal B, which is going to be greater than E, which is going to be 0. All right, and that's kind of like the idea of path of least resistance. No, the current is not going to go only through the path of least resistance. What's really going on is more of the current, when you have a parallel situation, more of the current goes through the path of least resistance, but some will still go through that more resistance path. So both bulbs A and E are removed from the socket. So this one's pretty interesting. So you would have our battery, C, D. There's no more path through E. There's no more path through A. So you're left with B, kind of stranded. And as you can imagine, no current is going to go through. No current is going to go through here, right? We have a closed. It's not a closed path. No current is going to go through B. So C and D, they're in series. They're going to have the same like brightness, but B kind of short circuits, I guess you could say, or in the sense that there's no more current that's going to go through B if you remove those little like wires, right? If you remove the bulbs from the socket. Both bulbs A and D are removed from the socket, so I don't have to actually erase this. I don't know why I'm erasing it each time. We're going to remove D. We're going to get E right back because E is in the socket this time. And A is still not in the socket. And yeah, this one's pretty straightforward. There's 3 in a series. They're going to have the same brightness. So C is going to equal E, which is going to equal B, which is greater than A, which is equal to D, which is equal to 0. Okay, so these 3, I think they're a little bit more hard to do it in the sense of like thinking about what's in series, what's in parallel. I'm able to solve these with Kirchhoff's laws and get the same result. But if anyone can do this without the voltage law, and I'm going to show you how I'm using the voltage law, please let me know in the comments because I actually have no idea how you do this without voltage law. But here's how I would approach when a wire is put across socket A. So we have, let's just do this. So we have D back. Now when there's a wire going through A, that doesn't mean, that literally just sounds like what it sounds like. There's a wire going through A. There's no more light bulb at A, just wire. Now, this one, I think, in my opinion, I think you could do it conceptually, and I'll talk about how you would do it kind of conceptually, think about it, but how can we mathematically prove, like, which one's going to be the brightest? I would use Kirchhoff's laws. So, Kirchhoff's loop rule, right, if you make a loop, let's make a loop right here. So, let's say I want to compare C and E. What I would do is I would say, okay, well, the sum of all those voltages is going to be kind of 0. So, when you're going through this resistor, you're going in the direction of the current, right? I know the current is going to go through this way. So, it's going to be minus I1R, right? So then, now, this way, let's say for E now, right? We're going through this loop. I don't know if the current is going up E or down E, right? Because really, if you can kind of think about it, maybe the current could go this way, maybe the current could go this way, I don't know. So let's just say it is minus I1R, right? Let's say this is the direction of the, up is the direction of the current. That would make it a negative term, because it's like, resistor taking up energy. I1R is going to equal 0. Well, that's not right, and I'll say I2, sorry. Actually, I'll use letters. So the current going through C times R minus the current going through E times R is going to equal 0. Well, that's not right. You can't have two negatives add up to 0. One of those has got to be positive, and it's going to be the current going through E, right? Because I know for sure current's going to go through C like this, right? We're going from positive here, and then the current has only one, kind of one way to go. E has to be the one where, in reality, the current's going down. Okay, so then really quickly I can algebraically be like, okay, I, E times R is going to equal IC times R. Great. The R's are the same. That means they're both going to have the same current. We know for sure mathematically these two are going to have the same brightness. Okay, so with that kind of thinking, you could apply that for all sorts of loops. Now, I know E and C are going to have the same brightness. Let's take a look at B, E, and D. How are those going to compare, right? So, I know that, okay, let's make a loop. Now that I know the current's going down E, I can make a loop like this. Okay, so, in a case like this, I would just use the loop rule again. So I know minus IE times R. Current's going to go through D, right? Because if you think about, I think in this case you might not need to do this, but whatever, I'll just do it. You're going to get C, you're going to get C, what am I doing? Okay, current going through C plus the current going through E, you're going to get D with current going that way. So it's going to be another minus ID times R plus, and okay, so here's the next thing, right? So I know the current is going to be going through B as well. So I'm going in the opposite direction of the current. That's going to be a positive IB plus R times R. Just IB times R. I'm just using Ohm's law to get that voltage. So then, if I just rearrange this, I can cancel out all the R's, right? Divided by R on both sides, you get 0. Or 0 divided by R, yeah. Okay, so we get IB is going to equal IE plus ID. In other words, the current going through B is the sum of the currents going through E and D. So I know for sure B is going to have more current than E and D. So then, which means B is going to be more current than C, because C and E are equal currents, right? So this is the statement right there. So I know B is actually going to end up being the brightest. So then we have the current going through E and the current going through D. Well, what I also know is from the junction rule, this is the current going through this is IC and this is IE. At this junction, they're both going to add up to the current ID. So I know ID, the current going through D, has to be bigger than the current going through C and E. So I could say B is greater than D, which is greater than C, which is also equal to E, which is greater than A, which is going to be 0 in this case, right? Okay, so conceptually thinking about it, this actually makes kind of some sense, because we're thinking, okay, if I'm current, this path is the one with the least resistance, right? And then if I go through C and then D, I would end, if I go through E and D, so D would kind of be, the current here would have, okay, wait, this is kind of like crazy to think about, because it's like, okay, D is only one resistor. If I go through E, I have to kind of go through 2 resistors. If I go through C, I only kind of have to go to 2 resistors. So then it kind of makes sense that C and E are like third. But then it's like, well, if I'm going through D, you know, I only going through 1 resistor. How is it not equal to B? And so it gets kind of confusing. That's why I like using Kirchhoff's loop rule. But if there's a better way to conceptualize this, please let me know. Without like loop rule, if there's any way I can do this without loop rule, that'd be greatly appreciated. I'm just going to apply loop rule for these last two when a wire is put across sockets C and E. So in this case, if I just redraw this, it's getting a little messy. In this case, I would have, so C, so when a wire is put across sockets C and E, so I would have something like this. So this one's pretty interesting. You could use the loop rule again, but really, what you kind of do is kind of be like, well, these two are in parallel, so I know these two are going to be the same no matter what. And now what's really interesting is sort of like the resistor is in parallel with the wire. Now in a case like this, the wire would kind of get all the current, right? This is where it's kind of that passive resistance thing, because it's like, okay, if I go through here, it's going to have some resistance. I'm going to go through here because there's no resistance here, and then B and D are going to be equal. But how do I confirm that with the loop rule? Well, with the loop rule, you would kind of be like, okay, let's make a loop right here, okay? So you're going to have minus the current, we're going to have minus ID times R plus I B times R, right? Because we're going against the current here. It's going to equal 0. So R's will drop. You get IB is equal to IB, right? So these two are going to be equal. Now let's say we make a loop like this. So we're going to have minus ID R, so minus ID R plus IB times R, and then plus, we'll say plus here, because, you know, maybe we're going against, IA times R. Is an all equal 0. But wait a second, I already know that IB and ID are equal. So if I, you know, if this is ID times R plus IB times R, this term already adds up to 0. So this just becomes 0. So you get 0 plus IA times R. That just means IA times R is equal to 0, right? In this case, that means there's no, the only way this can be true is if there's no current going through A. So you kind of get a short circuit situation here. And no current's going through A, and these two are going to be equal. So you really get B is equal to D, which is greater than everything else. A is equal to C, which is equal to E, which is all going to equal 0. All right. So when a wire is put across socket A and bulb C is removed from the socket. So really, you have, okay, let me kind of just erase this and get a fresh start. I know this video is getting long, but it might be helpful because the answer I got had like no explanation, so that's why. And I just had my thing rubbed on this equal to. Okay, So, oh, this is greater than, oops. So, if we think about when a wire is put across sockets A and both C's removed from the socket, no, so back with like the removing the socket, that kind of cuts off the wire, so we get something like this. And this one is actually pretty straightforward because we just kind of get that same scenario where you have two in a series, so they're gonna have the same current going through them. So I know E is gonna equal D, and then this equivalent resistor is gonna be greater, and it's gonna be in parallel with this resistor. So if you have in parallel, greater equivalent resistor means less current. B is gonna get the most current. Yeah, so B is going to get the most current. I don't know why I lost my train of thought, which is going to be greater than E, which is going to be equal to D, which is going to be greater than A and C, which are both equal to 0. So yeah, that was kind of the problem. Yeah, so let me know if there's any way you could do this without Kirchhoff's loop rule. I would appreciate that. And thank you for watching. 21 minutes, yikes.